Thank you very much. I'd like to thank the organizers and Lucas in particular for the kind invitation to be here. These are my disclosures. I think I submitted them electronically, so you can read the full list there. Flow diversion is a really exciting field in particular because it was well described in the preclinical research before it became commercially available to you. There were over 40 peer-reviewed journal articles, the first of one which appeared in the early 90s that discovered this effect where you could redirect flow cause thrombosis of the aneurysm, but the curative event is when a new blood vessel grows over the scaffold, permanently excluding the lesion. And we understood from an engineering perspective exactly the mechanism of how flow diversion works. Blood goes through your body, through your vascular system, from the high pressure side of the heart to the low pressure side of the heart. This is called pressure-driven flow. But flow goes into an aneurysm for a different phenomenon. The blood flow has inertia. And when there's a change in the boundary, it carries that momentum. It's called momentum transfer into the aneurysm. That is not a pressure-driven flow. It's a different fundamentally. The only time there's a pressure gradient is when the aneurysm is ruptured and it's bleeding into the brain. So you can leverage this mechanistic understanding to develop technology that can disrupt the momentum transfer yet preserve the pressure gradient, because as you often know, there's perforating vessels near these aneurysms or large arteries, and they require that the flow diverting device does not alter that pressure gradient and obstruct blood flow there. I'm going to skip these. Sorry, I had removed them before the talk. One of the things that we did not predict when we were developing these devices is we were very good about getting optimal apposition of the flow diverter. And this is some great work that came out of Mayo Clinic where they looked at these rabid aneurysms that had been treated with flow diverters, and on DSA there was no detectable malapposition. But if you looked at the histological section of this aneurysm that persists, is still filling, you can see that there was not optimal apposition. So we decided to study this using optical coherence tomography. It's an intravascular imaging technique. And we saw indeed that looking at this cross-section, the picture on the right, you can see where this is the neck of the aneurysm. And the device is not well opposed to the aneurysm neck at that level. And we wanted to see that if early occlusion of the aneurysm, if communicating malapposition was a factor. So on the top case, you see a very well opposed flow diverter at the level of the aneurysm neck and complete obliteration of the aneurysm at 30 days. Whereas here, a very similar aneurysm, even smaller neck, had communicating malapposition, so an endoleak, if you will. And at 30 days, it was completely patent. So we found with our data analysis that in the presence of communicating malapposition, you were much more likely to have at an early time point persistent aneurysm or patent aneurysm, whereas a lot of the data could be explained if you didn't have communicating malapposition, you had a very high rate of cure. So what's the next big thing in flow diversion research? And that is, there's two mechanisms by which you have platelet aggregation on the surface of a flow diverter. The first is the fact that it doesn't belong there. It's a foreign body. So the platelets recognize it and they respond to it. The second thing is that when you deploy a flow diverter, even in the best hands, you cause injury to the endothelium. It only takes about 300 dyne per centimeter squared. That's a very small amount of force to cause disruption of the endothelium. And you expose the subendothelial matrix, which is highly thrombogenic. So technology is about biomimetics that's coming out with these different devices to hide the flow diverter from the body. I want to make it perfectly clear that the first technology that we have available is not a coating, it's a surface modification. This is the pipeline shield technology, where phosphorylcholine is chemically etched into the surface, creating a 3 nanometer thick structure of phosphorylcholine. It's important to understand this is not a coated device, rather a surface modified device. We studied this using 50 rabid aneurysms. Half of the animals received the control device, the other half received the shield device. And we used optical coherence tomography to examine thrombus formation in the acute setting. And so here's an example. We defined 3 areas. We binary coded whether or not thrombus was present. And we also looked at the orifice of the side branch. This is a source of thromboembolic complication if you have platelet aggregation at that level. And what we found is that more important than dual antiplatelet therapy in preventing acute clot formation was this shield technology, hiding the device from the platelets. You can see that we had lower scores, and more importantly, over the orifice of side branches, you could dramatically reduce the acute platelet aggregation on the surface of the device. This has been published. You can read about it in JNIS. but importantly, Shield significantly reduced the presence of acute clot formation and reduced the presence of this clot at the orifice of side branches. There's another novel hydrophilic coating that has come on the market in Europe that is not yet in the United States. This is also using a biomimetic concept. Your endothelium are covered with what's called the glycocalyx, and so they've coated this device with a polyglycan, and the idea being to mimic the endothelial cell. And so what you can see is that it's incredibly hydrophilic. The bottom device is coated, and you don't see the water drop. It can't maintain its surface tension. And here they did an in vitro assay where they could show that the coated device dramatically reduces what you see in yellow here is platelet aggregates. And you can see that when you have a coated device, you dramatically reduce the amount of these platelet aggregates. And so we did a similar assessment. Now this is using optical coherence tomography that has recently been developed in collaboration with Gentuity. It is the same size as a micro guide wire, similar to an 014 micro wire, but it has the optical lens and we can image inside the blood vessel. It's specifically built to image in the neurovascular system. We implanted 3 pigs with coated and uncoated devices. We had different antiplatelet algorithms for each animal, and we acquired the data, and here is in real time using this new optical coherence tomography. You can see that with the coated device we have very little acute clot formation, whereas if you look at the control device, you can see a lot of acute clot formation along the surface of this device. And of course we measured that. We measured the volume of clot present. So here an uncoated device, clot present, here nearly occluding the side branch. And I want to bring this out. You cannot see this angiographically. So even though this vessel looks patent, you can see more than 90% of the orifice of that vessel is occluded. And here's what our data tell us. We could, with the use of this coating and a single antiplatelet medication being aspirin, we could remove 99.8% of the thrombus burden. I am out of time, so I will just give the credit where credit is due, which is I have an incredible group of people at UMass, and thank you very much for your attention.